Hi everyone, welcome to STMPC's FPGA Development Series. As we all know that FPGAs are the integral part of our industry. We have so many applications of FPGAs for commercial, for industrial purpose, or even in military grade and in research. Now why FPGAs has so many applications? And that is because of its architecture, which gives us freedom to customize the board as per our requirement. Now as a hardware design engineer, if you want to grow in the industry, you should have some understanding of FPGA development as well as some programming skills, for example Verilog and Python, which you can use to optimize your work as well as do certain measurements using SKP standards, etc. So that is why I'm starting this FPGA development series, by which we can have certain understanding about FPGAs and its development process. Now before starting this video, I want to thank ALINX.com for providing Zynq7000 hardware as well as all the support throughout the preparation of this series. So let's get started. Let's start this video with a small introduction of FPGA. So FPGA stands for Field Programmable Gate Array, and the entire architecture of FPGA is divided into two units, PS and PL. Here PS stands for Processing System and PL stands for Programmable Logic. And within these PS and PL units, Xilinx has many architectures which varies application to application. For example, they also have Zynq 7, UltraScale Zynq, UltraScale plus Zynq, and then they have the portfolio of Spartan and RTX FPGAs. Now in this video, I'll introduce you to very popular architecture of Xilinx FPGA, which is Zynq7000 series. Now as we have discussed earlier, Zynq has a very wide range of portfolio of FPGAs and it is just the beginning. So Zynq7000 series is a sort of good starting point to understand more about FPGAs and its development. Alright, so let's start with that. Like you can see on your screen, this is the Zynq7000 architecture, and like other FPGAs, this architecture is also divided into two units, PS. So PS, within the PS, where we implement all the software part of the development, alright, and within the PL we implement all the hardware part or custom logics. And there is some interface between PS and PL by which we can communicate between these two. As you can see on your screen, for example, this extended multiplexed I/O or EMIO. Then we have multiple GP ports, and GP stands for general purpose. Then we have high performance ports as well. Alright, so we use these interfaces to communicate between PS and PL. Alright, now further, as you can see in this architecture, we have subsystems within the PL and PS units, as you can see in this block diagram. Now I'm going to highlight some key subunits in the PS. So let's start with APU. Here APU stands for Application Processing Unit. So APU is nothing but a processor integrated within the FPGA SoC. In Zynq7000 series, it is dual core, but it can have many more cores based on processing requirements. So in one word, APU is the one which controls all the functions within the PS. Now within the APU we have MMU as well, which stands for Memory Management Unit, and which translates physical addresses to virtual addresses and vice versa. Then we have this data and instruction cache memory. Apart from that, as you can see, we have memory controller to interface external RAMs, but we have a small integrated RAM as well, and its capacity is 256 KB, and here OCM stands for on-chip memory. So this on-chip memory is there for all the low latency applications. Apart from that, we have this 8-channel DMA. So DMA stands for Direct Memory Access. Now it is useful to dump large amount of data. If we'll process that data through memory units, then that will keep our processor busy at that time. So to avoid that, we use DMAs, so CPU can perform other stuff during the large data transfer. Now here I'm just mentioning all these blocks and giving some small overview, but if you are interested in a very detailed explanation, then you can simply go to the Xilinx website, and there you'll find Zynq 7 documents, and within those documents you'll find all the information in very detail. Next we have this central interconnect. Central interconnect is nothing but the bridge between IO peripherals and memory, PS and PL interface and the memory, etc., which is a sort of self-explanatory from the block diagram. Now another important block in the PS is General Interrupt Controller or GIC. So GIC take care of all the interrupts coming from PL as well as from the IO peripherals. And based on these interrupts, we can do certain operation in the PLs. Alright, next move to the programmable logic or PL. So PL is nothing but the FPGA where we do hardware level customization, and which we'll see in detail during this series. So in short, within this programmable logic unit, we make a customized hardware, and that can be anything. For example, if we want to do certain debugging, we can customize or create our own integrated logic analyzer within the PL, which we can use to debug the hardware. Alright, so we don't need to use external logic analyzer. So that's the advantage of FPGA. And how we communicate between PS and PL, and for that we have these interfaces which we have already discussed. So that's it from the architecture side, and let me know in the comment section in case of any questions. In the next step of this video, I'm going to talk about the entire process we follow for FPGA development, and after that we'll set up our own design environment on a Windows machine. So let's start with this process. So the development of Zynq is also a hardware first software approach, and the specific process is as follows. So first we'll create a new project on Vivado and add an embedded source file. In the next step, we'll add and configure some basic peripherals of PS and PL in Vivado. Then we generate a top level HDL file in Vivado and add the constraint file. So constraint file is the file where we assign all the actual pins to our software. Alright. And then we compile and generate the bitstream file. So in the next step, we can simply download these bitstream file when our board is connected in JTAG mode. Alright, and then you can see the execution of that program on your board just after this step. Now if you want to boot from SD card, then the next step is we export the hardware information to the SDK software development environment. So in the SDK environment, you can write some debugging software to verify the hardware and software combined with the bitstream file. Alright, so you can individually debug the Zynq system. Then in the next step, we generate the FSBL file in SDK. Then we generate the uboot.elf and bootloader image. And for that, you can use VMware virtual machine if you are using Windows machine, because you need Ubuntu for that. And then we generate a boot.bin in the SDK through the FSBL file. We generate system.bit and uboot.elf file documents. Then after that, the 8th step will be to generate the Ubuntu's kernel image with Zimage and Ubuntu's root file system, and that will be doing within the VMware. And in addition, it's necessary to write the drivers for FPGA custom IPs. Alright, then after that we'll have the last step, and that is put the boot kernel device tree and root file system into the SD card. Alright, turn on the power of the development board, and Linux operating system will boot from the SD card. Alright, so this is the entire process of FPGA development which we follow in almost every application where we are using Linux. And I know it's a lot to do, and that is why I'm starting this series. Alright, so here we'll learn from very basic, like writing a hello world program, and then we'll be writing some complex image processing application later part of the series. So let's start with setting up the Vivado development environment on your Windows machine. To set up the Vivado environment, we have to follow certain steps. So first we'll open just Google Chrome or any other browser which you'll be using on your Windows machine, and then search Xilinx there. Then you have to go to the downloads link of that Xilinx website. And for ALINX development board, we got a lot of examples and demo files or demo projects from the manufacturer or the ALINX.com, which will help us in development. So what we'll do, we'll just follow their criteria, and their criteria is it is good to use Vivado Design Suite 2020.2 version instead of the latest version available. So we'll just go to the archive, select the 2020.2 version, and from here you have to download the single download file. Alright, so I don't know, I've already reported this issue as well. When you're trying to install from web installer, you'll be getting some error. Alright, so to avoid that, I will highly recommend to use single download file. It will take some time, but it will work for sure. Now after the download is done, I'm going to extract the downloaded file. Now once the extraction will be finished, you have to double click over installation. Then here you'll see this pop-up window of continue without upgrade. So let's select that, and we are going to select Whiteys because when you'll install YTS, the Vivado will come with that. So after certain projects we'll be using YTS as well. So let's select YTS here, agree to all the terms and conditions, and click over install. So during the installation process, there will be so many pop-ups for installing the device drivers and couple of third-party softwares. So always click on install those, because during the process we need those device drivers. Alright, so those device drivers are nothing, just the DigiLent device drivers. So that will recognize our board when we'll be starting our development process or writing firmware for that. Similarly, we have to click over this install WinPeak app. So what this installation will do, it will install all the low-level drivers that extend the operating system to provide low-level network access. Alright, so install that as well. And once the installation is done, we'll go to start menu and run the Vivado 2020.2. Now apart from that, I just want to highlight one more jumper configuration for this ALINX 7020 board. And here we have this jumper J13. Make sure it is connected to the JTAG mode, not from the SD card boot mode. Alright, because for next couple of videos we are just going to flash the .bit file or bitstream file directly into the development board from our computer. Alright, so we are not going to follow the SD card boot procedure as of now. Alright, that we'll do later at the later stage of this series. So make sure that J13 should be connected in JTAG mode. If you are using any other development board, so make sure to check the configuration. It should be in JTAG mode. Now in the next step of this video, we are going to run Vivado, and there we are going to create our very first project. To do that, we'll go to start menu, and from here you have to select Xilinx, and there you'll find this Vivado. We'll just click on that. Then we are going to create new project from the quick start menu. So just click over this create project. And here we have this new project wizard will open. Alright. And here first we'll just click over this next button. I'm just going to rename this project first project, and let's save it on desktop. So I'll just go to and just select ALINX FPGA Development folder in my case. In your case it can be different location, and just click over this select button. Make sure you have selected create project subdirectory, so it will create this first project folder inside the folder, and that is very useful to segregate different projects. Otherwise all the files will be just opened inside the FPGA development folder. Alright, and then click over next button. Here make sure you have selected RTL project, and that will give us freedom to add or create new source file, block designs, IP integrators, etc. And that is not possible with other options. So make sure to select RTL. So after selecting RTL projects, click over next button. Now here it is asking us to create source file, which we are going to create later. So for now we'll just leave it blank. Target language in our case will be Verilog, and make sure the simulator selected should be mixed. So in this entire series, our focus is to learn Verilog for FPGA development. In your case, if you want to learn different language, you can select VHDL from here. Alright, and then click over next button. Add constraints, that we are going to do later. Click on next. Okay, this is very important part. Here we are going to select our SoC. So in our case, first we have to select the family from here, which is Zynq7000. Then we have to select the package, and this information you'll find on the top of the chip. So if you'll just check your board, and there we have this Zynq SoC sitting there. Alright, and if you'll just see there, you'll find these certain part number written there. Alright, so in our case it is CLG400. Make sure you have selected that, and then we have to select the speed grade, which is -2 in our case. So for Zynq7020 it is -2, but if you are using 7010 development board, then it will be -1, and this is our part number. So make sure you have selected that, as you can see on your screen as well. So I've just highlighted this chip, and there it's written the part number, which is XE7Z020 CLG400. Alright, select that and click over next button. And here we have our project summary. Just go through with that. Make sure you have selected correct project option and correct part number, and click over finish button. So once the project file has been created, in the next step we are going to create the source file, which will be .v extension, and there we are going to write our code for LED blinking, which will light up for 1 second and then turn off for another 1 second, and that will be in infinite loop. Alright, so we are going to do that. Now to create the source file, we'll just go to this project manager, and from here we'll find this option add sources. We'll just left click on that. Now here we have to select add or create design sources. Click over next. We are going to click over this create file. Now I'm going to name it LED blink. Make sure you have selected the same location, which is local to project, so it will go in the same folder where we have the project file. Alright, and then click over OK button. Here we go. So we have created the source file here, and then finish. Now it is asking us to define the input output parameters, so that we'll do later. So we'll just click over OK, and so currently the constraints file will be empty. And here we go. So here we have this design source file, which is LED blink. If we'll double click here, we have this empty module sitting here with the time scale. We'll discuss what it is and what is the purpose of this time scale here, and how to write code in Verilog for LED blink. But inside the constraint, we have empty as of now. So after writing the code, we are going to define all the actual hardware, which will be assigned to different variables defined in the code. Alright, so we have to basically make connection between actual hardware and software through this constraint file. So that we'll see how we can do that. Next, we are going to write the Verilog code, which will be blinking 4 LEDs on our development board, as you can see on the screen. Now before moving further, I just want you to introduce to the schematic. So from that, we got to know when these LEDs will light up and when these LEDs will turn off. So for that, I'm just going to open the schematic, and from the schematic, let's jump to page number 12. And here you will find these PL LEDs. Now as you can see, the other side of the LED, or the positive side of the LED, is connected to 3.3 volt. Alright, and the negative side of the LED is connected to PL side of the FPGA. So that means when these LED 1 to LED 4 pins will go low, the LED will light up. So if you want to see where these pins are connected, because anyways we have to assign the correct pin number to all the variables we are going to create in our code. So let's go to page number 5, and there you'll find this. I'm just going to zoom in a bit. And here you'll find this LED 1 to LED 4 pins are connected to M14, 15, K16 and J16. So we are going to assign these pins to our LED. Now since we have the schematic, I'm going to tell you one more thing. And here we are going to use counter, and that counter will count. So that will be a 32-bit counter. It will count from 0 to 50 into 10 to the power 6, and that will be 1 second. So this is how we are going to count the time. We can also block the code for that time using time scale, but let's do that counter thing. So how this 50 megahertz will be 1 second, and that is because of the PL clock. So if we'll just search PL clock, or if we'll just search 50 megahertz, and here you'll find this PL clock, a local oscillator is connected there of 50 megahertz, and that is going to define the clock of those PL LEDs. Alright, so we are going to use this as a reference clock, and our counter will count all the rising edge or falling edge of the clock, and based on that there will be increment, and after 50 into 10 to the power 6 counting, the LED will change its state. So this is the logic we are going to use during our Verilog code. So let's go back to Vivado. So start with the very first line of the code, which is time scale 1 nanoseconds / 1 picoseconds. So this is the time scale directive, which gives us brief idea of how many time steps unit you are considering. So for example, currently it's 1 nanosecond. So if you'll use #5 somewhere, it will block the control for 5 nanoseconds. Similarly, if you are just writing, let's say 5000 somewhere, then it will block the control for 5 microseconds. Now you can ask, what is this 1 picosecond? So picoseconds denote the resolution or precision of this time value to rounding off the time. Alright, so next we are going to discuss the module. So this is a sort of definition, we call it module definition, and within this module we basically define all the input and output parameters. So whatever we'll define, let's say inputs or output within this module, we have to assign hardware pins to those input and outputs. So for example, if here we have denoted 4 LED variables, then we have to assign those 4 LED pins which we have discussed in this previous steps, right? Or if we have defined the let's say a variable reference clock, so that reference clock will be connected to the same pin where we have this PL clock connected of 50 megahertz, right? So here we have to define all the input and outputs which are going to connect to the hardware, and that is the module definition. And after module definition, we write our code where we use all the local variables, all the logic, or always block, etc. So that we'll discuss when we'll be writing the code. So here first I'm going to define all the input and output parameters, and I'm going to do that quickly. So as you can see here, we have first input, which is a sys clock. It's the same 50 megahertz clock. Then we have reset pin. So this is the reset pin which is on our board, all right? And this is a PL reset. It's another switch. So when we'll press that, the entire board will go into reset state, all right? So we'll just use this condition in our always block. Like if we are resetting the board, then counter will reset. So we'll just use that for this purpose. And then we have this LED, 4 LEDs defined as an output. So we are going to assign the state on these LEDs. So the idea is whenever the counter will cross 50 megahertz, the LEDs will change their state. And here we have defined 4 LEDs, which are LED 0 to LED 3. So this is the way to define the output. Next, we are going to define the local variable, which will be the 32-bit counter. Here we go. And after that, I'm going to create an always block. So always block is a sort of while loop, you can say. So it will just always execute whenever these conditions will met. So currently the conditions are positive edge of sys clock or the negative edge of reset in. So whenever the reset will go low, so by default the reset is high. That means the board is not in reset state because it is active low reset, all right? So reset will be active when we'll just connect it to ground. So currently it is pulled up. And whenever the control will see the positive edge of the clock, this always block will execute. And after writing the always, we always type begin, and then after begin we can add our conditions. So I'm just going to write the first condition, which is here. So the first condition is if not reset, or if reset is connected to low, that means our board is in reset state, then all the LEDs will go low. So here we are assigning decimal 0 to all the 4 LEDs here. So this is the sort of notation or syntax we use for assignment together to all the number of variables. And similarly, we are doing this with timer counter. So this is a 32-bit counter. So we are going to assign 0 to all the 32 bits. And this is when our board will be in reset state. Then we are going to type another condition, which is if or else if the timer count is greater than or equal to, so all the 32 bits counter will be greater than or equal to, because it is starting from 0. So that's why there is 1 minus from 50 into 10 to the power 6. All right. So then when we just crossed the counter, then what we'll do, we'll just toggle the LEDs. So that means the 1 second is done and it will just begin this statement, which is LEDs will be assigned to the complementary of LED, whatever the current state is. So let's say by default the LEDs are off. Then after this counter will meet this condition, it will turn on the LED and the counter will reset. Now we have to write the final statement, which will be else. So let's go here. All right. Else the LEDs will contain their default state and the counter will increment by 1. And at last we have to end our always. So we have to type one more end, and that's it. Our Verilog code is ready. So this is pretty much straightforward. And yeah, let me know in the comment section if you have any question from this block of code. Yeah, the logic is pretty much simple. So next we are just going to save this Verilog code and it will update everything here. So currently we don't have any IP core or anything integrated with this Verilog code. So we'll just see nothing changes here. Now in the next step, we are going to define all the hardware pins, or we are going to assign all the input output pins to our variables, which are system clock, reset and 4 LEDs. Now to do that, we'll just go to open elaborated design. So this is a sort of schematic, which is a bit hard to understand here, but if we'll just follow these traces, you can able to see what is happening exactly in terms of flip-flops. So here we have several D flip-flops we are using. Yeah, and here we have these FLs conditions and some complementary, which is switching the state of LEDs either low or high based on the conditions. We'll not discuss that. We'll just go back to our Verilog code. And to open the input output manager, we'll just make this window a bit bigger and go to Windows. And from here we have to select IO ports. Alright, let's expand these. So here you can see we have these outputs and inputs defined here, and from here we can assign the pins. So if you remember the schematic, since I've already noted down the pin number for LEDs, reset and sys clock, but I'm just going to show you on the schematic one more time on your screen. So as you can see, these are all the LED pins. This is the reset pin and this is the system clock from the schematic. We are going to assign these LED0 to LED3 variable, reset and sys clock variable. So LED3 will be assigned to J16. So let's type J and from here select J16. LED2 will be assigned to K16, and these are all coming from the schematic. So if you don't know these pins where these are originally connected, then you can't do this assignment. You have to contact your manufacturer. From them you'll get the correct pins which you can assign here. Then we have this M15 and the last LED pin is M14. Let's connect that as well. Then we have this reset which is connected to N15, and the system clock or the 50 MHz clock is connected to U18. So as you can see, as soon as you'll assign all the correct pins, here we'll see this, the color will change to some yellow color and you can see the check mark here. Now the job is not done yet. We have to assign the correct voltage here. So currently it is assigned to 1.8 volt, but if we'll check the schematic, you'll find all these pins are connected to 3v3 logic. So let's select LVCMOS 3.3 volt and same here and that's it. Next we are going to save this constraint. To do that, we'll just click over this save button, and here we have to type, let's say, the same LED blink, or you can just name it anything, and the extension will be XDC for these files, and click over OK. Now you can go back to source file. Now again I'm going to minimize this a bit so we can see, and now the constraint file is created. Now the constraint files are again some sort of assignment of pins as well as the voltages to different variables in terms of physical real connections. So if we'll just double click on this, we can see these sort of statements here. So set property package pin J16 will be assigned to LED3, similarly for other parameters, and same for the IO standards LVCMOS 3.3 volt will be assigned to different variables. Now after these constraints assignment, the next step is we have to assign the timing constraint. So currently our software doesn't know the sys clock is 50 MHz, which we have to define by typing the constraint, or again defining the physical connection between the variable and the clock speed. Now to do that, we have to run the synthesis first, or which is a sort of compilation as well, and click on OK. It will take some time, which you can track here, or you can see this is running here, synthesis. We are not going to implement this synthesis, so we'll just cancel that whenever it will ask for running the implementation. Now as you can see, after the completion of synthesis, it is asking to run the implementation. We are not going to do that because the timing constraint is not defined yet, so we'll just cancel this. Then we'll just open this open synthesized design, and here we'll find one option which is constraints wizard. We'll just left click on that, and this wizard will automatically detect the clock pins which we have used in our or defined in our module. So currently it is sys clock, right? And now here we have to define the correct frequency. So in my case it is 50 MHz, and based on that frequency it will just calculate the period rise time or fall time, which you can add as per your real clock. You can introduce jitter as well, and based on that it will run your or execute your code. So we'll just leave it default, just add the frequency here, and just click over skip to finish, and then click over finish. Now again go back to your constraint file, and here it is asking us to reload this. We'll do that. Now here we have this timing constraints defined. So everything is done from our side. We have written the code, we have made the physical connection by defining the constraint. Now in the next step, we are going to generate the bitstream file. Now there are further steps as well, which is simulating your code as well as doing the debugging after flashing or uploading the bitstream file, which we are going to discuss in detail in the next video, because it's again a separate topic and I want to discuss that in a sort of detail with the correct process. So I'm not going to further extend this video, and this code is pretty much straightforward, and I have run that couple of times and we have done the execution as well, so we didn't find any compilation error or anything. So we'll just click over this generate bitstream. Now it is asking us to update because we have added the timing constraint as well. So click over S and we have to again launch the synthesis and implementation. So click over OK button. So once the writing bitstream is done, as you can see here, we can see this pop-up window which is asking us with couple of options. So make sure you have selected Open Hardware Manager and click on OK button. So this will open Hardware Manager, and here we can connect our board. So as you can see on your screen, we have already powered on the board. Now I'm going to connect that. So we'll just click over this open target and click on auto connect. Now this process will automatically detect the board with the obviously using COM port, and it will make the connection. And after that we can program our development board with the code we have written here. So as you can see, the board has been detected here, which is XC7020, and you can see the status is not programmed. We'll just right click here, click over program device, and it will automatically direct us to the correct bit file which we have saved on desktop, or this is the project folder. So we don't need to do anything here, and click over program button. So as you can see, all the 4 LEDs started blinking, and obviously the duration is the 32-bit counter, which is running from 0 to 50 megahertz, which will be 1 second for LEDs. So the LEDs are on for 1 second and then off for 1 second. Now to verify that, you can just change something in the design, and you can just play along with this code and see how this is reflecting on your actual hardware. So that's it for this video. For the next video, as I've already told you, I'm going to discuss in detail how to run the simulation before programming your actual hardware, because that is not safe. You have to first verify your code and then we flash that. And after flashing, if we need to do real-time debugging on your board, so there is one integrated logic analyzer, which is an IP core. So we'll see that how to use that. So that we'll discuss in next video. Now, in case of any question, please drop your comments in the comment section. Reply to those ASAP.